Okay, hello everyone. I think this is the last discussion. So we have the uh, eigenvalues, right? Repeated eigenvalues, and if we have multiplicity 3 by 3, right? And before that, let me just show you something that might be interesting. So in GeoGebra, I found there is a source that you can make the face portrait, but it's on the 2 by 2 matrix. So if you check the matrix here, the coefficient, and then you can try to move out all this axis. So if we take, for example, the red line will be the eigenvector, which be calculated from these two values. Okay. And if we have this, we have two eigenvalues, two eigenvectors. So if we can change this to the repeated eigenvalue, which you can, I have tried that, but let me just show you what it means and how we can actually take the, for example, this is the eigenvectors, and you can see that well, I think there is another sources that you can change the slope field, maybe make it more discrete, or maybe make it more continuous, and you can see that it has these four quadrants, that it has their own characteristics. Okay? They have their own characteristics, and for some interval, for example, interval on this left side here, then we can have some, well, depends on which boundary we have. Maybe here you can have this line, and then basically how you line it up is just make it like assumption, based on assumption, because this slope is basically our approximation for a smaller scale. To make it more the approximation more accurate, then we need to make the arrow more smaller and smaller, and then we can make it more smooth in terms of the face portrait. So basically, this is just an illustration on how we could also try to make out our 2 by 2 matrix in GeoGebra. You can find, I think you can just find through GeoGebra, find resources, and then my keyword is just face portrait. There are some, I think I found 3 or 4, I forgot. You can check face portrait, or you can check eigenvalues. They have, I think, another forms on the resources. Okay. Okay. Anyway, I think for today's class, I will just go for some examples, okay? And then, if we have time, we move to the complex eigenvalue. And if we finish all of that, I think the last part on the how to solve this system of differential equation is one last method, is we call the using diagonalization. Okay, that will be the last part on this system of differential equation. I'm still thinking to include the non-homogeneous part, which we have covered in the engineering math 1, but I think there will be too much content for you, so I will just look for exercise, because I look at least the 3 by 3 eigenvalues problem, and I believe to solve 3 by 3 takes really much time, although by calculation it's not too difficult, but you need to be aware and careful when you calculate, okay? Because when you are doing it wrong, maybe you are not getting any eigenvalue or eigenvector. Okay, maybe you are going to be lost somewhere, like your quiz. So I think maybe for exercise, I think it will be good if you can done the 3 by 3 matrix easily to find the eigenvalue. Okay, let's go through our example here. So now is the I think I will start the easy example for the repeated eigenvalue. So let's say we have this. Okay, I think, have we done this before? I forgot.
Oh, not yet. So this is 3 by 3 matrix, and this is supposed to be the repeated eigenvalues. How do we know that? Because this part here, if we look at the diagonal, it's all the same, and we have the lower triangular is 0, which means that the determinant will be on the diagonal. So it means that if we take the determinant a minus lambda I, which we are trying to use that for eigenvalue, we are going to have 2 minus lambda cubed. We multiply 2 minus lambda, 2 minus lambda, 2 minus lambda. And basically that. So we know that this will be multiplicity 3. So there will be three eigenvalues with the same value. Right? Okay, so let me write. Okay, so since I'm right here just to make sure that we are remembering the matrix property. So since the lower, or maybe just write since lower triangular matrix or this is supposed to be since this is, let me write this is, since this is, then you can write the determinant a lambda I equals 0. This is equal to, or let me just write directly 2 minus lambda cube equals 0, or we can write that the lambda, or is basically 2. Okay, or let's say write lambda 1 just to name the symbols. Okay, lambda 1, and then taking this into the equations, we get, and then taking the a minus 2I k, this will be 0. So 2 minus 2 will be 0, 1, 6, 0, 0, still 5, 0, 0, 0. And I think this will be easy, right? Very easy. So we get this 0, 0, 0. And basically this is our augmented matrix. So we have K2 plus 6K3 is 0, K3 is 5, and we could say this is, we can make it, or let me just solve the 5 and I think 6 and make it clear. So 2, is there anything wrong here? Okay, I think it's supposed to be okay. And you'll see that we can make the second row become 0. So, well, we could take the, or let me just solve this directly. So K3 is 0, 6K3 is plus K2 is 0. So let the K3, so K2 is also 0. So K2 and K3 are 0. So the only way this could work will be the single eigenvector. So this, we can work this is 1, 0, 0, and then solving the a minus 2I p, and then solving the next one. Okay, so basically we are going to take the P1, P2, P3. So suppose that this is, so 2 minus 2 is 0, 1, 6, 0, 0, 5, 0, 0, 0. 1, 0, 0. Let me check again. Okay, so perhaps this is going to be oh, let me just multiply with the 6 over 5. Let me minus this 6 over 5. So this will be 6 over 5, 0. So I will multiply the R1 with the 6 over 5 and then minus the row 2. So this will be that. Okay. So we have, this will be, it could be this, okay, for the P. Well, you can have some combinations, okay? You can have this, or you can have, so you can have the P, so this is P2 is 6 over 5, P3 is 0. So 0, 6 over 5, 0. And then using the same P, so there will be some combinations for this, and you could choose those values, and then this is supposed to be here, and in the same way we write again. Now we can, I think, multiply with the 5 over 6. Let me resize all of this. So this can be 6 over 5, right? 6 over 5. Now 6 over 5. I will multiply 6 over 5. Yes? Now this will be 6 over 5. 6 over 5, right? Minus subtraction, 0. So 0 minus 36 to 25. Well, my combination is not really good. 6 over 5. And I think this can be, the Q2 can be 6 over 25. Q3, sorry, Q2 is 36, 25. Well, that's, I think another combinations, I think this is bad number. And it's not easy to computerize for a fractions like this, so we can choose another number, okay?
Wait a minute.
Hmm?
For the left one.
Mm-hmm.
If I divide by 5 and times 6 and count it, the I have some less will be 1.
Oh, right. Which one? This one?
The 6 over 5
Mm-hmm.
is 1.
Oh, this one, right? Oh, yeah. Okay. So this will be, so 6 over 5 should be 1, right? This one, right? Is that true? 6 over 5, subtract. Oh, yeah, 0, right? 0, yeah. Okay. So that's why I feel that this number is not really good numbers. Okay, we can pretty much doing it again. So we have P2 is 1, and I think we could agree that this will be 0, 1, 0, right? Okay, and then we could write that as our another Q for Q. So this is 5, and we take it again and make it the other Q. So actually we are trying to find a combination of number that is going to be related with each other. So first is the P, the second is the Q. So this will be, and then this will be very, I think, very similar. We can take the, I will make this 0, so 6 over 5 again. So let's 6 over 5 again, and then I will subtract. So subtract 0, 1, 6 minus 6 is 0. 0 minus 6 over 5. 0 minus 6 over 5 is, so this is negative 6 over 5, right? And then what else? This is still 0, 0, 5, and 1, 0, 0, 0, 0. Or I will write this is divided by 5, okay, it's 1 over 5 like that. So this will be Q3, 1 over 5. Q2 is negative 6 over 5. Okay, I think nice. Now the number seems reasonable. So the Q, let's say Q1. Well, not Q1. Maybe it will be difficult to distinguish. Just Q will be 0, negative 6 over 5, and 1 over 5. Okay, so we have everything. P, so we have P, we have Q, we have K. Okay, and now to write down the general solutions, we're going to have a little bit long equations. Okay, So bear with me. So the general equation will be x. Let me write here. The first one is the K1, so C1, 1, 0, 0. The eigenvalue is E with 2t. Okay. And the second one, so this is a pattern that is supposed to be in repeated eigenvalues. Okay, so if we have multiplicity 2, remember that we have eigenvector 1, constant 1, and then the second part will be constant 2, but we have 2 eigenvectors. For 3, we have 1, constant 1, and we have constant 2, we have 2 eigenvectors, and we have constant 3 with 3 eigenvectors. Okay, so that's I think pretty crazy if we are dealing with the 3 by 3. So C2. This will be we need to include again 1, 0. Sorry, I think the best way to remember how the pattern works is like your engineering math 1. So when you have the repeated values, you multiply and then you write 1, and then the other part is the linear independent, right? But the way we work in this eigenvalue, this will be the eigenvector. Okay, the one that is k. This is kp, kp cubed. Okay. If you have a 2 by 2 matrix, you have k and then kp. So this is the constant 2. Write again the k, but to make sure that this is going to be linear independent, this is not the same with this, so we need to multiply with t for this one. So write t e with power of 2t, and then plus the next part will be the p, 0, 1, 0, and then e 2t. And then we close the bracket, so that's the second solution. The next one will be the constant 3. Still, we are going to bring back our 1, 0, 0, the k, but since we have e, and then the next one is pe, then what's supposed to be the next part? We need to multiply, but the way we multiply, we are having t squared over 2. If you remember the engineering math 1, the best way to remember that, perhaps if you check this, you integrate, it's going to make this. That's how you make sure. Okay? So if you have like a more, then you can imagine you can take that down and then add some constant to multiply and then make it corrections. And then plus 0, 1, 0. But 0, 1, 0, we have now e. Next one here will be t. Okay. So as long as you are having recognizing all the patterns, I think it should be okay for the repeated value. Okay. And then the last one will be 0. And this will be e to t. And then close bracket. Okay, that's the solutions. Okay, quite a lot, and yeah. But always remember, the questions or the problems might be combinations. Maybe you have a distinct eigenvalues and you have some multiplicity. So I think the best way to solve, or the best way to write the solution, maybe you find first the distinct eigenvalues. and then you have the repeated values. But you need to check whether they are linear independent or not. It's also need to check. So perhaps this is for the multiplicity, but maybe if the question has the distinct eigenvectors, then you need to add one more. You need to add one more component that is maybe distinct eigenvectors. Okay, maybe later if we have time for overview, we can take some time to practice. And if you find like exercise doing the repeated eigenvalues without boundary value, without initial problem, there will be some combinations. For example, you have distinct eigenvalues and then you have the repeated values in the same, maybe combined together. Because we are not defining which one is the constant 1 and constant 2. So maybe you could have like the repeated first and then the distinct at the back side, or maybe the distinct eigenvalue here, and then the C2 and etc. will be the repeated eigenvalue. It can be a combination like that. So I think there will be some combination. But the thing is, we are going to see the eigenvectors and then this the E. That's the, I think, the clue for whether you can confirm your answer or not. Okay. I think I need to go to the complex value for a while, and then on Friday we can have some overview, and then maybe we can take some practice for the eigenvalue. Ah, wait, I forgot. Oh yes. Okay, so that means that, okay, next Monday. Okay, I also forget. I forget the dates. Okay, let me mark. Okay. Okay, so let me continue the complex eigenvalue. Okay, just for a while. So I keep this exercise. This is the one that I will take some time for exercise. I will add more for preparations. This is the same with this one. This 4 here, I'm trying to solve maybe next week. Okay. So start with the complex eigenvalue. So suppose that we have this example. So we have dx dt 6x minus y, and we have dy dt 5x plus y for y. So if we take the determinant and then try to find the eigenvalues, this will be this will be 24 say minus 5 plus, so lambda squared minus 10 lambda plus 29 equals 0. And this will be, I think, easier to take this as 25, right? So this will be negative 4. So this will be lambda minus 5. This will be negative 4. So we have lambda minus 5 is plus minus 2i, right? So we have lambda is 5 plus, lambda 1 is 5 plus 2i. Lambda 2 is 5 minus 2i. So we have a complex eigenvalue. And then we check for both value. So for lambda 1, 5 plus 2i. Then we take 6. So 6 minus 5 plus 2i. Or let me just write, this will be 1 minus, right? 1 minus 2i k1 minus k2 equals 0. And then 5 k1. And then 4 minus 6 is minus 2. So minus 2 minus 2i, or let me write this, 1, sorry, minus 1, minus 1 plus 2i, right? K2, right? Right, okay, correct. Okay, erase. Equals 0. And then solve this. So from there we have k2 equal 1 minus 2i k1. So we can let k1 equal with some value. So let k1 equal 1, which means that k2 will be 1 minus 2i. So we have then the k1 is 1 minus 2i for the eigenvectors. So the solutions for these eigenvectors will be 1 e, and then our eigenvalues is 5 plus 2i t. Okay. And then the second part will be the second value, 5 minus 2i. And you will see that this will be giving 1 plus 2i. This will be giving you 1 plus 2i, k1 minus k2 equals 0. So k2 equal 1 plus 2i, k1, which gives you an idea that if your k1 is 1, then k2 is 1 plus 2i. So that means the second eigenvector should be 1 and 1 plus 2i. Then your solutions is 1 plus 2i e. This will be now is 5 minus 2i t. And this, I think we can also verify. We can verify through Wronskian. Wronskian is how we check the linear independency using the Cramer's rule. Okay. Check linear independency. So we have the general solutions. C1 okay. And you will see that we have the since the eigenvalues are conjugate, which means
This is 5 plus 2i, 5 minus 2, and you see that this eigenfactor also, it is also conjugate, 1 minus 2i, and then 1 plus 2i. So we can
write something about that. Okay. That it will works for the other case that is complex, okay? Because complex is going to have this plus minus, since it's related to the quadratic discriminant property, right?
But what we want, if you remember what we did in engineering math 1, we don't want to show the imaginary value. So we need to using the Euler formula with cosine and sine and some sort of that. But that is actually, if you see the pattern, it has a pattern that we can follow. Well later I will show.
Yeah, I think since now it's already March 25, and I think the second week of April will be scheduled for exam, right? Midterm exam. So exam, I think the matrices, eigenvalues with this system of differentials, and perhaps up until if we finish the complex, and then we add one more, just one small subtopics from still in this eigenvalue. I think that will be the whole topics for exam, for midterm exam. Okay? So it's all about matrix and system differential equation with matrix, eigenvalues, and later the diagonalizations. We call it diagonalization. It's also the method to solve the system of differentials equation. Okay? And then after the exam, the half course later on, we are going to focus on the factor calculus in terms of the integrations, okay, the line integral, the surface integral, the Stokes theorem, divergence, etc. So you are going to see again some part of the integrations, double, triple integral. If it is going smooth, I'm trying to add a little bit of either partial differential equation if the time is sufficient. Okay? But if not, then only the integrations will be okay. Okay, now let's go right here that since this is conjugate, okay, so this is conjugate. So all the terms in the complex, it has some conjugate. So we can write the theorem that we could have so this is going to be the conjugate. So this means it's conjugate. And then, since we want to make the Euler relations, let me write here. This will be E 5t This is cosine 2t plus I sine 2t. And then the conjugate we can write and then we can replace C1 plus C2 by C1 and C1 minus C2I by C2. Okay, so we take this, and we get this. Okay. And then we can write as x C1 x1 plus C2 x2, where the x1 is 1 cosine 2t minus 0 minus 2 sine 2t. And then multiply with the e with 5t. Or this will be cosine 2t, cosine 2t, right here. Plus 2 sine 2t e 5t, and then x2 0 negative 2 cosine 2t plus 1. Basically we just take turns. But now it's this sine 2t negative 2 cosine 2t plus sine 2t. Or we could just write like that. Okay. Okay, actually, this theorem hasn't finished yet, but I will just show you. This is the result that we want. There's something in between that haven't yet proven. Because we need to we need to connect. Okay, we need to connect the eigenvector, and then need to generalize the whole system. Okay. Let me just copy this. Okay, copy this. And just add some additional notes. Okay, let me just write again here. Right here. So from this x, and suppose that we have the k1 e lambda 1 t, we can write as k1 e, and then we can define the lambda becomes alpha and beta, as in Euler equations, and this can be written as K1 E alpha t cosine beta t plus I sine beta t. And then the conjugates, let me just write the same thing with conjugates the bar on K and eigenvalue. This will be the same, all the same, but the difference, the beta will be negative beta. This is the same. And then this will be cosine beta plus or minus I sine beta. And then we are taking the superpositions principle. Then superposition principle. Then we can have the x1 will be half K1 E come down 1t, and then plus K1 conjugate E t, and then this conjugate. Okay, the same thing with x2. We are doing it the same way, but now we have I over 2. And basically, this will be equal to and write all the Euler terms. And then define that we have B1 and B2 is this. Okay. Quite long and intimidating, right? So, but by the end, we could simplify the complex and removing all the imaginary number by taking at this real solutions. Okay, so we write all terms with real number through the Euler formulations. So taking the superpositions, you could have this. Okay. So that's it for now. We are going to see you again later on. Okay.